All right, so we got the human cannonball question. Okay, part A wants us to find their gravitational potential energy relative to the ground when they're at the highest point in their flight. Okay, so there's a couple of ways for me to do that. Okay, to find their gravitational potential energy at that point. Okay, I could find his kinetic energy at that point and subtract it from the mechanical energy, which I could calculate at the very beginning. Right? Because at the very beginning, I know he's moving at 21 meters per second. I know he's 15 meters off the ground. I could easily go, mgh plus 1/2 mv squared and know his mechanical energy. In fact, that's what B is. We'll need that for B as well. But finding the mechanical energy is one of the things we have to do. Okay? For part A, the two ways for me to do this are to find his total height, and use that to find his potential energy, or to find his kinetic energy at this point and subtract it from the mechanical. Right? Either one of those ways will get me the potential energy. Everyone all right with that? Okay. So if I'm going to do the maximum height way first. Right? So if I want to find his maximum height, here's what I have to know. Okay? I've got him being fired at 21 meters per second at 20 degrees above the horizontal. This side of the triangle represents the initial vertical velocity. This side represents the horizontal component. Does that ring a bell from kinematics? Yeah. Okay. If I'm going to calculate his maximum height, that occurs here when VF is 0. All right. So if I want to calculate his displacement, I need to know what VI is. I know what the acceleration is. It's 9.81. All right. So I'm going to calculate VI the same way I would have back in the kinematics unit. I'm going to go sine of 20 because it's the opposite side times 21. Okay, so the initial vertical velocity is 7.18 meters per second. All right, now I can use this formula to find D. I do, it's 9.81. Yeah? Okay, so I'm going to subtract, I'm going to go VF squared minus VI squared over 2A equals D, and then I'll know how high he gets above his starting point. Okay, so I'll have 0 minus 7.18 squared. And then I'm going to divide that by 19.62. And that should be negative. All right, so the height that the human cannonball reaches above his launching point is 2.62 meters. I have to add to that 15. Now, can I calculate his potential energy? I have mass, I have his height, and I have acceleration due to gravity. All right, so this times, what was his mass? 56? I multiplied by 15. Sorry, I should have added by 15. Okay, there's his height. All right, so I'm going to take that, and I'm going to multiply it by his mass, 56 times 9.81. Okay, so there's his potential energy at that point. Okay, 9.684 joules, or sorry, 9,684 joules. Everybody all right with that? Okay, the other way to have done this would have been to calculate V horizontal. That would have allowed me to calculate his kinetic energy here, and then I would have subtracted that from his total mechanical. Okay, that would have been the other way. They're about the same amount of work, so it really doesn't matter which way you would have chosen. Okay, everyone all right with that? So you had to just incorporate one thing from the last unit in order to calculate mechanical energy.
Can you show how to do it the other way?
The other way? Okay, so I would have taken cos of 20 times 21. That would have got me, that's the horizontal component of the velocity. Okay, so what I'm going to do now is find the kinetic energy. So I'm going to go 0.5 times 56 times that squared. Okay, there's his kinetic energy, and then I've got to calculate his initial mechanical energy. So I'm going to go 56 times 9.81 times 15, okay, plus 0.5 times 56 times 21 squared. And then I'm going to subtract.
2 squared also 21.
Oh, 21, sorry. Ah. Okay, get the same answer. Yep. All right. The net in which he lands is 2 meters above the ground. How fast is he traveling when he hits it? This is just a conservation of energy question. Okay, how many people have had a chance to even start? Okay, I'm going to give you a few minutes to start. You don't need any projectile motion stuff to do B. Okay, you just need to do a conservation of energy question like the Evel Knievel question we did yesterday. You're calculating his speed when he hits the net, which, reminder, is 2 meters above the ground. Okay, so it's an EI equals EF question like we did the other day. Give you a few minutes on that. So here's what we need to understand in order to solve part B. To solve part B, I have to understand that the mechanical energy at the launch point and the mechanical energy at the landing point are equal. Okay? So I can say that the initial mechanical energy and the final mechanical energy are the same number. Okay? I calculate mechanical energy by taking initial potential, adding it to initial kinetic. That's going to equal final potential plus final kinetic. All right. What I'm looking for is how fast they're going when they hit here. Which of these terms is that part of? EKF. Right. It's part of this. It's part of the final kinetic energy. So what I'm going to do is before I put in the formulas and I have all those letters and everything, I'm going to move this over here. Okay? Easier to move it now before I expand. So we're going to have initial potential plus initial kinetic minus the final potential equals the final kinetic. Now I'm going to expand these out. Okay? Now I'm going to put in all the formulas. So m times g times h initial plus 1/2 mv initial squared minus m times g times h final equals 1/2 mv final squared. Ready with me so far? Okay, this is just like a roller coaster question from Science 10. It is. It's just exactly the same. Now, I want to solve for VF, and I'm seeing that even though I have the mass of the human cannonball, that it's in every term. What can I do with it? I can get rid of it. Okay, don't need it. Saves me entering stuff into my calculator and possibly making a mistake. All right, now, I want to get VF by itself. What do I do with the 1/2? Divide it. I want VF, not VF squared, so I square root. Then I can plug in my numbers. So 9.81 times 15, because that's the launching height, okay, plus 1/2 times the initial speed, which is 21 meters per second. And that's got to be squared. Minus 9.81 times the final height. The net is 2 meters above the ground, so I've got to include that. Then I'm going to divide that by 1/2 and square root the whole thing. Okay, so we've got 9.81 times 15 plus 0.5 times 21 squared minus 9.81 times 2 divided by 1/2. Okay. Oh, what did I mess up?
Brackets.
No, the 0.5.
Oh yeah, I don't have a 0.5 there. All right. 26.4 meters per second. That's even what they got.
Yeah.
Okay. Now follow what I did. Just roller coaster question from Science 10. Just it was a human cannonball instead of a roller coaster. Okay, all works the same. All right, with a pendulum. Never mind. Okay, suddenly this is going to be really cool. Okay, this is ghetto physics, by the way. Okay, because well, when you cut money from education, this is what you get for demos. Okay, you get the drawstring I took out of my hoodie and a roll of athletic tape. Yeah, like a pendulum from a scientific company called $50, and it just swings back and forth like this. If you like a fancier one, write your MLA and tell them stop cutting money from education. My teacher has to use a drawstring and a roll of tape to make a pendulum. Yeah. Okay, so a pendulum swings back and forth. Okay, just swings back and forth. All the time it's swinging, it's converting potential energy into kinetic and kinetic energy into potential as it swings back and forth. Everyone okay with that? Yes? Okay, where does it have the most potential energy? Right, here and here. Right? It has the most kinetic where? At the bottom, in the middle. Okay, so here where it stops, like where it changes direction, it has how much kinetic energy? None, right? Okay, its velocity or speed, is 0 at this point, and its height is at its maximum value. Here, its height is at its minimum value, and its speed is at its maximum value. Okay, and so that's all that happens with a simple pendulum. It's just converting, okay, one form of energy into another. But the amount of mechanical energy is always the same. Okay? Because as potential is converted to kinetic, that number stays the same all the way through. Okay? So we have this ideal pendulum that is 2 meters long. It's pulled sideways and released. At the highest point of its swing, it's 25 centimeters above the floor. Do I want to keep that in centimeters?
Probably not.
Probably not. Okay, I want it in meters. So basically what they're saying is this point right here is 0.25 meters above the floor. Okay, the lowest point the pendulum is half a meter above the floor. Or sorry, it's 5 centimeters above the floor, so that's 0.05 meters. The mass of the pendulum bob is 250 grams. Incidentally, that's the thing that's at the bottom of the pendulum. The mass at the bottom of the pendulum is called the bob. I don't know why. That's what it's called. Okay? The bob. Yeah. All right. What is the mechanical energy of the pendulum relative to the floor when the bob is at its highest point? Okay. What kind of energy did we say it had at its highest point? Only potential. Can I calculate that?
Yeah.
Yes. Just by going m times g times h. Okay. So that'll be 0.250 kilograms times 9.81 times 0.25 meters, because it did say relative to the floor, right? And it was 0.25 meters above the floor. So our potential energy, and thus our mechanical energy, is going to be 0.613 joules. Okay, what's the mechanical energy of the pendulum relative to the floor at its lowest point? Same. 0.613 joules. Okay, this is a trick question. Okay, the mechanical energy is conserved. It doesn't change. What is different is how much of it would be kinetic. There'd be very little potential and a lot of kinetic at that point. Okay, what's the kinetic energy of the bob at its lowest point? That I'll have to do some calculating for. How am I going to figure it out? Okay, I have the mechanical, and I would subtract EP, right? So mechanical energy is kinetic plus potential. I can calculate the potential at the bottom because they told me the height at the bottom. So all I would do is go 0.613 minus 0.250, the mass, times 9.81 times 0.05. Okay, that'll give me my kinetic energy because it's bringing the EP over to this side. Everybody all right with that? Okay. What's the speed of the pendulum bob at its lowest point? Well, once I have the kinetic energy, so we'll go points, so we'll just use our answer there. All right, so there's our kinetic energy. And I solve for how fast it's going now. Yeah, divided by half of m and square root. So 0.125, because it's 0.25. Okay, and then square root that. All right, so at the bottom of the swing, it's going to be moving at 1.98 meters per second. Okay. Now you can guess. All the interesting stuff's happening. So. Okay, I want you guys to try question number 2 here. I'm going to make it bigger so you can actually see it. Okay, so you got a model rocket that has a mass of 3 kilograms. It's fired so that when it is 220 meters above the ground, it is traveling vertically upward at 165 meters per second. At that point, its fuel runs out. So now, no more work is being done. No more energy is being put into the rocket system. Okay? So the rest of its flight is without power. Assume that the effect of air friction is negligible. That's their way of saying use the law of conservation of energy for this question. Okay? And that all potential energies are measured from the ground. So A, what is the mechanical energy of the rocket relative to the ground when it's 220 meters above the ground? Okay? And when it reaches the highest point in its trajectory, what will its gravitational potential energy be? And then how far above the ground is the rocket at that point? And then finally, when it hits the ground, what will be its speed? There's a lot less calculating in this than those questions make it seem. Okay? Give you some time on that one. Okay, so we got this model rocket. The first thing they want us to find is the mechanical energy of the rocket relative to the ground when it is 220 meters above the ground. Am I essentially calculating the mechanical energy anywhere when I do that? Yes, I am. Okay, anywhere at least after the fuel runs out. The mechanical energy will be that value. So, I want to calculate that mechanical energy. I'll take the potential energy at that point and add it to the kinetic energy at that point. So, our mechanical energy will be m times g times h plus 1/2 mv squared. And we know all of these numbers. Okay, the mass is 3 kilograms times 9.81 times 220 meters. Add that to the kinetic energy, 1/2 times 3 times 165 meters per second, and that's squared. Okay, so 3 times 9.81 times 220 plus 0.5 times 3 times 165 squared. All right, so we're looking at 47,312.1 joules. Now, we only have, 3 significant figures here, so it'd be 4.73 times 10 to the 4 joules, okay, which is what they have there. Okay, part B, when it reaches the highest point in its trajectory, what will its gravitational potential energy be? Okay, I fired this thing straight up in the air. When it gets to its highest point, how fast is it going? 0, which means all of its mechanical energy is now potential, which is why the answer is 4.73 times 10 to the 4 joules. All of the mechanical energy that we already calculated will now be potential. Okay, that's what I was saying. This looks like it's a lot more calculating than it really is. Okay, there would have been no way to actually calculate that number. We wouldn't know how high it is. We'd have to calculate that and then calculate. So there would be a way. Why would we do it? We just recognize here. Okay, it saves us a lot of time. Okay, for part C, how far above the ground is the rocket at its highest point? Okay, well, here's how much energy it has. It's all potential, so I'm just going to say 47,312.1 joules equals m times g times h, and I'm going to solve for h by dividing both sides by mg. So I'll take that number I calculated and divide it by 3 times 9.81. All right, so it's at 1.61 times 10 to the 3 meters, so 1.6 kilometers approximately. Everybody follow what I did there? Okay, I just said all the mechanical energy is potential, and I calculated the height using the potential energy formula. Okay, and then for part D, when the rocket hits the ground, what is its speed? Okay, when it hits the ground, all of its energy will be kinetic. All right, so then this number, again, is now my kinetic energy. So 47,312.1 equals 1/2 mv squared. Divide both sides by half of m, square root, and I'll be calculating the speed of the rocket when it hits the ground. So all right, so it'll be moving at 178 meters per second. Everybody follow what I did there? All right, it sounds like when you read it, like there should be a lot more to all those calculations than there is. Okay, but this is one of those questions where if I really understand the law of conservation of energy, I can save myself a lot of work and a lot of time. Okay. All right. All right, I want you to try 3 and 4 here. They are ones that I would give Science 10 students. I don't say that to insult you. I say that just to be honest. Okay? So, first one's a roller coaster, second one's a pole vaulter. Okay? They're both law of conservation of energy questions, treating pretty much the same. Give you a few minutes on those. The answers are right here. You want to check and see if you did them right. Okay, so here's what we need to realize about the roller coaster question. It's still saying this. This is still true. The mechanical energy on the first hill is the same as the mechanical energy on the second hill. Okay, that still means initial potential plus initial kinetic equals final potential plus final kinetic. Now, they want me to find this, not part of it. Actually that. They want me to find the kinetic energy. They're not asking for the speed. They're asking for the kinetic energy. So if I want to get that by itself, what do I do to EPF? Subtract it over. All right, so I'm going to have EPI plus EKI minus EPF equals the final kinetic energy, which is what I'm looking for. Now, I can plug in my formulas. M times G times H initial plus 1/2 MV initial squared minus M times G times H final equals EK final. Okay, that's what they want me to find. So now I just plug in my numbers. So we'll have, so the roller coaster control at 840. So 840 times 9.81 times 85 meters plus 1/2 times 840 times 0.2 squared minus 840 times 9.81 times the height of the second hill, which is 64 meters. All right, when I do that, that should get me my final kinetic energy. Okay, 1.73 times 10 to the 5 joules. Okay, that makes sense to everybody? Probably easier than what you were making it out to be. Okay. Usually people overthink that one, and they try to find speed and they can't figure out how it's not something we needed. Okay. All right, for question number 4 here with the pole vaulter, okay, we know their mass, 56 kilograms. In the pole vault, you're trying to convert kinetic energy essentially into potential energy, right? So there's actually a number of conversions that go on in the process. First, you run as fast as you can while holding a big long pole, okay? Then you jam the pole into this hole in the ground, and it stops the pole. Now, the pole is made of fiberglass, so it bends, okay? All of your kinetic energy changes the shape of the pole and bends it, turning it into elastic potential energy. Then, as you rotate and pivot, okay, the pole will convert that potential energy back into kinetic by flinging you up and over the bar. Okay? But in the end, all we're doing is converting the kinetic energy of our running into potential energy as we go over the bar. Okay? Everybody follow me on that? Right. Now they've simplified it a little bit in that we're supposed to assume that their speed is 0 as they go over the bar. Okay? That's not exactly true. If your speed was 0 when you approached the bar, you would fall straight back down, and that's where the hole you stuck the pole into is, and you'll hurt yourself really badly. Okay? I've seen like pole vault go horribly wrong a number of times. Okay? Especially when people get the pole twisted in their hand, because only one side of it bends. It only bends one way. You turn it in your hand, and you try and bend it the other way, it'll snap. And it'll snap right when you're fully committed and upside down. And you fall on your head. Okay, try this. Okay, that's not happening in this one. In this one, everything goes perfectly. And the person flies over the bar.